Howdy, everybody. Hope you're doing well wherever, whenever you are. Um, the I think the rest of the year is probably going to be different for puzzle solving. I just got a lot of family activities and stuff like that, and it's really hard for me to like take 2 hours out of the day and do like a just like sit down to solve a problem. So, uh, especially if I can't solve the problem, which we're talking about Quest 9, but I did do Quest 10 as well. So you'll see that posted shortly. And man, I had some bugs in Quest 10 that had me going for like, I probably spent 4 to 6 hours on it. You wouldn't have wanted me to see me solving that one. Anyway, so just so you're aware, I think it'll be more of a recap of how I solved it and you know what the key insights I had, and you know, that we can talk about more your solutions as well and stuff like that. So I think too I like this because it'll give me time to like maybe explain the theory or the reasoning or the intuitions better, as opposed to just like you watching me type and try things. So as you probably see in my videos, I am not fast. So anyway, we'll move to this style maybe later if we feel like it's interesting enough. We can do like the live solves, you know, by doing like an actual stream or something like that on a weekend or something when I have time. But in the meantime, I still want to get these out because I really enjoy your comments and your ways that you solve them. It helps me get better at this too. So I'm gonna keep making videos. Just the format's gonna change a little bit. But with that, let's get talking about the day. So it's encoded scales, and you do a lot of stuff with it's like the mimicking DNA sequencing is what it is. It's not quite how DNA works, I don't think. Other than like, I mean, I guess I haven't. It's been a while since I've seen. I don't think it works this way, but it is a cool idea. Anyway, let's get to it. So in part one, the gist is you have a bunch of DNA sequences and you're hoping it will help you like find your lineage or relationships and stuff like that. The stories, by the way, I think are pretty cool. So, you know, on par with Advent to Code and stuff like that, where you feel like it's not just like you're solving a puzzle, like a problem, you're like in part of a story solving it. So that's fun. But the idea is you're given these DNA sequences like this. And the idea is, given these sequences, can you find parent-children relationship? And the way you find the relationship is you say, given two parents, do the sequences of those two parents cover the values of the child? That is, the child must inherit each of its values in the sequence from one of the parents. It could be both, but it could be one. So if you're looking at these three, it kind of tells you, it says like, oh, so if you assumed that this was the child at first, that actually wouldn't work because the second position has an A and the other positions have a T. So there's no way that these two parents could have produced this A, if that makes sense. That's where I say like these are a little bit like gene sequences, but I don't think that's exactly how it works in the real world, like in biology. I think it's slightly more complex, but I could be wrong. If you're a biologist and you literally just XOR the things together, or like and the things together, that's cool. Let me know. But anyway, the idea is you now know that this one can't be the child. So you have to ask yourself, okay, well, is this one the child or is this one the child? And if you kind of go through those same steps and you say like, oh, okay, well, 2 couldn't be the child either because both of these have an A, which means this number 2 dragon duck couldn't be the child. So we from that we can kind of conclude that in this case it's number 3 that's the child, and these 2 must be the parents. And if you go through that process, you see like C, T, A, G, C. Like for each of these values, one or both of the parents have that value. And so what they say is figure out which one is the child and which two are the parents, and then do this matching analysis, like find the similarities between each child and each parent, and then multiply those together. So now that we found the child, we can say, well, how similar are they to the first parent? And then how similar are they to the second parent? And multiply them together. So that's it for part one. So what does that look like in code? Well, what I did was I said, okay, I'll create this sequence with an ID because you're given their IDs and you use them in later parts. And then I'm just going to keep a collection of characters. I also I implemented from string. I'd forgotten about this. We've done it before, but implementing from string actually makes it really cool because you can do things like where do I do it? Somewhere in here. Oh, it's in the input parsing. I can just do map sequence from for a string and it will do it. And that feels kind of cool, right? I know a lot of people use nom, or there's a competitor nom whose name I'm forgotten. But anyway, this is kind of I implemented from so that you could easily parse. And I don't always do that, but I think it is a cool tool to just say, if we impl from, we can do things like into and from pretty easily. Okay, so for part one, really you just have to ask yourself, because there's only 3, right? Even if you go look in your own input, there's only 3. The number of sequences, or the number of like values in a sequence, is much longer, but there's still only 3. And so for me, it was just easy enough to say, okay, well, I just need to determine, are these two the parent of this sequence? And basically that's saying for all the pairs, is the child value covered by one of the parents? So that's what this is doing here. We zip together all 3 of the sequences, and that gives us like our parents as well as ourself, and we just say, are all of them covered by one of the parents? Excuse me. Once we figure out the parent lineage, we need to then just count their similarities, right? So that's another simple iteration. We just zip together our sequence as well as the other one, and we filter by how many of them are the same, and then we count those. So pretty simple tools. This is one of the things I like about Rust, is you can do things like this with its iterators. So I think a lot of people like functional programming, like Haskell and Lisp, because you can do cool things like this. It almost feels like magic. And so anyway, yeah, I utilized those. This we use later. I'll talk about that later. But so then for part one, the solution just is, I'm going to get 3 sequences, and because there's only 3, I'm just going to do the tests. So I say, are 1 and 2 the parents of 0? And if they are, multiply their similarities. Well, okay, are 0 and 2 the parent of 1? And if they are, multiply their similarities. Otherwise, just we now know that for sure 2 is the child, and so we'll multiply the similarities of it to its parents, which are 0 and 1. So that felt pretty easy because there's only 3. There's just only 3 states. We don't have to worry about it. So that was part 1. Not too tough. This is my answer. Yours will vary, obviously. For part 2, it got a lot more interesting because what it's saying is like, oh, now there's a whole bunch of them. And so now it wants you to see, can you, it's not just 7. It says there's 100. You have 100 sequences. They want you to like find relationships. So you can see here, as you can say, like, oh, this one has a big relationship, this one has a relationship too. Um, and then they want you to find the relationships or find the sum of the degrees of similarity of all the children found on the list. That's the goal, right? So you're essentially building a family tree, if that makes sense. So like, what does it say? So like, given these 7 right here, if you iterate through all the possible ways, you'll find that there's 3 children along with parents. So like 3, 1, and 4 are the children out of this thing, right? Here's parents to here. These 2 are parents to 1 and 4. And so basically what you do is you say like, you then do that same similarity comparison to get their values. So 3 has a similarity with 6 and 7 of 462 when you get their similarities and multiply them. And then 1 with 2 and 5 gives you 399, and 4 with 2 and 5 gives you 384. So that's how you get to those things. This changes the problem inherently to some degree, because now, you're going to be given 100 sequences. And so you can't just do a little, oh, well, I'll just check and find out which one is the parent. You now have to like do this over a huge span of things, right? If you think about what you're doing, you're basically taking sets of 3 and saying, well, is there a parent-child relationship between these 3? Like similar to what you did like for part 1, but you're doing it for all combinations of 3 of the 100, which can get pretty big, right? There's not really an optimal how do I say this? There's not really like a known optimal way to do this as far as I could tell. What that means is your solution is that, and what I'm talking about right here is still kind of n cubed, right? You still have to like for each sequence go through all the other sequences of parents, possible parents, and check and see if there's a relationship. The one thing that I found that made it faster, you can see over here that I was able to solve it in like, still in like just a couple of milliseconds, was you can pre-compute the relationships. So it turns out that computing the relationships is actually kind like when you're doing the n cubed part, most of the time in the n cubed is spent checking the relationships, right? You're literally looking through the string, and think about it. You have to go through the whole string to ensure that a relationship exists, because it could be the very last one that says, oh, this relationship can't exist. So the thing that helped me was to say, okay, well, what if I pre-compute all of the values? And so that's what this first thing does. Interestingly enough, they were exactly 128 values long. The sequences were of size 128. So I had the idea to practice my bitwise operations and store them all in a bit mask. And so that's actually what this thing does here, is this function on the sequence says, if you give me another sequence, I will return you a bit mask of all of the values where they overlap, right? So, and the way to think about that is like, these overlap means that like they cover each other, right? So like if the 1 position was set, that would mean that they both had the same value in the 1 position. If like the 8 position was set, that would mean they both had the same one in the 8. If the 4 wasn't set, that means they had different values, okay? So I'm literally going to do that for all combinations of 2. So that is n squared, but now I'm doing it like outside of the loop, right? And so now that I pre-calculated them, I don't ever have to calculate them again. And then what I can do is, now I can do my n3 loop, n cubed loop, right? So like for each parent and for each other parent, I can then go through all the values and say, go through all of them again and say, is this a child of parent 1 and parent 2? I can do that substantially faster though now, because I can do it with these like bitwise operations, right? I can literally just say what values are missing from parent 1. Like, given a child, what values aren't covered by parent 1, and then I just need to make sure parent 2 covers those. And this, so now what's happening is I still have an n cubed loop, but I'm really just like looking at array values and comparing them. So it makes it absurdly faster. I'm not kidding. It went from like 3 to 4 seconds to, you can see, like about 2 milliseconds. I think this was the thing that like saved me the most on part 2. You'll notice here I do a callback, and that's because I'm going to use this find relationships in part 3. But again, just the idea is, if I pre-compute the bit masks for each of the relationships, it's then very easy for me to go in during my n cubed loop and just do some bitwise operations, right? And what is that saying is like the similarities between anything that's missing from parent 1 has to be covered by parent 2. And if it is, then we found a relationship and we can build that thing. So that's like the key thing that helps you solve part 1 and 2. And it's actually the slowest part. We'll talk about an algorithm in part 3. But like if you look at part 3, it takes like 158 milliseconds. Most of the time in part 2 and part 3 is the work done in this find relationships. The part that isn't the rest of it, which is like getting to the answer for each of the parts, doesn't take much time at all. And so arguably, like, figuring out the optimal solution for this part is going to have the biggest effect. Okay, but let's talk about it. So what is the callback for part 2? Well, it just wants you to find the sum of those relationships, right? So the sum of the similarities of all the relationships. So you're basically doing part 1, but you're doing it for every single parent-child relationship. So what do? I just say every time I find a relationship between a child and 2 parents, I'm going to get their sequences from our array and then, sum up all of their values right here, right? I had thought, and it might be fun to still try and do, you can turn anything into an iterator. It might be interesting to make this an iterator. So as opposed to having a callback, you have it be an iterator itself. I may go do that in the recap. Just so we can kind of see what it would look like if you implemented this as an iterator. And what the way that you'd think about it is our next call would basically do this work until it found another value and then return that. But then we would just be keeping our state of like these 3 values as well as our masks. So I don't think it would be too hard to do, but it would be an interesting thing to do. So yeah, I think that's it for part 2, right? Is like the key is, how do you find these relationships efficiently? And then once you do, it's just a matter of computing their similarity score the same way like you did in part 1. I think that's all I want to say about that. Yeah. Okay. So what changes in part 3? And this one, because I figured out, I kind of I I'm trying to remember how I did this because it was a couple days ago. I think for part 2, I actually was just doing the loop because the size was small enough. It wasn't until I say the n cubed was small enough that I was still able to resolve it relatively quickly. It wasn't until I got to part 3 that I was like, oh, now I got to do something crazy. And like, why do I say that? Is because now you have 500. So 500 cubed is much different than 100 cubed, right? So at this point, it was running for like, I don't know, a couple minutes, and it still didn't finish. I'm like, okay, I got to do something better. And that's when I came up with the find relationships function, where I said, okay, I'm just going to I'm going to pre-compute, and then afterwards I'm going to do the stuff. So what changes in part 3? Well, now you're given 500 values, and now they want you to say, I want you to find the largest contiguous family, right? So imagine you have these 7 again. You know that these are the families and these are the families. So this one has a family size of 3 and this one has a family size of 4. It's the biggest family. It's the largest contiguous family. And so it wants you to return the sum of all their IDs. Okay? And this is where this is at the point where I said, okay, I got to find a more optimal solution of like finding the families or finding the relationships. And so I did that, and I that's when I fixed my find relationships part, right? So that's when I fixed all this code and got it solving. I ended up, when I first solved it, I actually just did a graph thing. I tracked parent-child relationships in a hash map, and then I just iterated through them and found the largest one. And it solved it pretty fast, right? Like you can see I'm solving now in about 160. It was taking maybe 250 milliseconds to do it that way. But this is a good problem for a disjoint union set, because if you think about what you're trying to do here, in like this thing is you now have a bunch of relationships and you want to track that those relationships and then find the largest. And this is exactly what a disjoint union set was implemented for. So I think here for part 3 we'll actually just talk about what a disjoint union set is. But like that's how you solve this problem, is you say, okay, well, I need to find an optimal way to find relationships. But like once I've found those relationships, how do I determine like the biggest group? And again, in this case, because there's only 500, the number is small enough that I think if you just did it in a graph and you did kind of like the equivalent of a flood fill for each of the values to like find the largest thing, which is what I originally did, works just fine. But I actually don't think, like I said, I don't think we've talked about a disjoint union set before, or a disjoint set before. And so I thought it would be fun to solve it this way, and we could go over how it works and what it is. So what happens is the idea is, again, we've like combined, we found all of these relationships, and so now we have like this relationship tree. The question is like, how do we maintain this state tree to know, oh, these 3 are in a relationship and these 4 are in a relationship? And again, disjoint data structure is disjoint set is a good way to do this. I think I keep saying disjoint union because it's also called a union find, but I'll try and call it just disjoint set. So here is the article. Oops. The Wikipedia article. And the gist of it is you want to maintain relationships between parents and children. And if you're able to maintain that list of relationships between parents and children, then at any time you can say, give me all of the things associated with this value. And it will hover up all the parents, and you can kind of go through all of them and connect them to their parent, if that makes sense. The idea is there's going to be one root node that's like treated as the parent of any grouping. And so whenever you add something to a group, it will be linked to that parent, and it may be over multiple things, right? Like at a high level, the way to think about it is you have like one value right here, and you know you want to add it, so you put it here and you add a link, right? Then at any time where you say, when you're like, hey, what group is this guy in, you work your way up to this one, which is the parent, and then you know he's in this group. And so when you add another value, let's say you add another value, it's over here, it's not part of it. Then you go and you add another value. Oh, but this one is part of it. Maybe it links here. Or maybe you go here and it links here, right? And then there's another one link that goes like here, right? At any point, you can say, hey, what member is this a group of? And you just kind of walk your way up the list until you get to the parent node, if that makes sense. And you'll create all these other ones like this that are over here. Maybe there's one off here by itself. They can look kind of wonky, but the idea is, here's our disjoint union set, and at any point in time, we can tell you like what value this node is a group of just by stepping up. And there's an optimal solution to doing this, or at least over amortized time is what they call it. It's called a disjoint set forest. And the idea is, I don't think they have, I may have to draw this. Yeah, I may just have to draw this too. You're really only interested in your relationship to the root node, like the quote unquote parent node. And so if you can kind of just manage an array of like which ones are parents and which ones are children to those parents, you can go pretty far. And so you start out with, let's say we have some list here, and we're going to say, 1, 2, 3, 4, 5, 6, 7, 8, 9. You start out with them all being their same value, and this means they're the parent. So when these two values are equal, they're a parent. So they're the root node. So they start out all being their own parents. Now, if you come in and let's say you now know that 4 is associated with 1. So we want to associate 4 with 1. What we do then is we update this value right here, and we say, oh, 4's parent is 1. So now whenever you ask the question, who is the parent, or what group does 4 belong to, it will jump over here and it'll say, oh, 4 is associated with 1. Now let's say 6, we say 6 is associated with 4. So what you'd normally do is you'd say, or what you will do is you'll say, okay, now we move 6 to 4, so now there's this association. So now if you want to know what group 6 is in, you say, oh, well, 6 is parent is 4, and 4's parent is 1, so 6 is in the 1 group. Does that make sense? And you basically just keep doing this over and over. There's an additional optimization you can do, though, and I'll show it in the code, and that's what makes it amortized over time, is as you're doing the updates, you can actually track the parents and update them inline. So when I said 6 is a parent of 4 and 4 is a parent of 1, you notice I went through that list. I can actually, though, as a further optimization, I can say, okay, well, I found out what the parent node is. The actual node is 1. So instead of putting 4 here, why don't I just put 1, right? And once you've done that, imagine going through this whole list. Well, now you know, like, say, for example, eventually you're going to go through the whole list, and it's going to look like this. It's going to say maybe 5 is its own. and 3 is linked to 2, and 7 is linked to 8, and 9 is linked to 8 as well. So given this, imagine this array, you now know which values are associated with each of the trees, right? Like these are the trees, or sorry, these are the sets within this disjoint set. So there's just, as we've gone through this, I want you to keep in mind that this works because the sets are disjoint. And so if we ever find a merging relationship, like if anyone were ever to come in and say, oh, 3 is actually related to 4, it would change this to 1. And now 3 is no longer related to 2. If you have these like branching relationships where there's like cycles or duplicate or like duplicate comings out, if that makes sense, then this is not a good solution for it. But this is a great solution for a quote unquote family tree, because you can build these disjoint sets, these little groupings that help you say, here's who's in this group and here's who's in this group. Okay, so I hope that algorithm makes a little bit of sense. Again, you could imagine if you had built a hash map with all the nodes, right? With all the parent-child relationships, like this. You could just traverse this. You could find a node in here and kind of traverse it and say, oh, this one's of this size and this one's of this size. And that will work. It just, on larger sizes, it takes time to do those calculations, right? And so doing it this way is potentially faster at the cost of, obviously you have a lot more memory. So, and I think it lines that out right there. Like when you're making the new set, oh, well, we can see it in the code too, right? So let's look in the code. So what does the disjoint set do? We need to keep track of the parent and the size of each of the values in the parent. Is that, yeah, why? Yeah. I don't think we actually need the size in this algorithm. But so what do? We keep track of our parents, and again, we start with them all being their own parent, and each of them are of size 1. That leads me to believe I might be able to optimize this. We'll try that in a second. So we need a couple operations, right? Remember, as we're finding relationships for our part 3, we want to create relationships, right? I do the -1 here because the disjoint union set is 0 based, and the but these values are like 1s based. These are the IDs, right? The IDs are 1s based. So we need an operation to like union them. That is to say, there is a relationship between C1 and P1, or C and P1 and C and P2. So what does that look like? And then once we do that, we need to go through and find all of the values, the values of those relationships. Yeah, I actually don't think I need to do this part down here. We'll talk about it in a second. Oh, no, we do, because it's the sum of IDs. It's not just the size, it's the sum of the IDs. Okay, so let's talk about this union operation. Well, how do we union two values together? Basically, what it means is, obviously, we need to find the root of I and the root of J. So we have these two values that we want to add a relationship to. We need to find out what their roots are, right? So who's the quote unquote parent? I think I call them root here. Yeah, I do, but obviously because it's right there. But they're the parents in the problem, right? So we need to find like the parent that bubbles all the way up, maybe is the way to say that. So we want to find both of those sides, and if they're already in the same tree, then we're done, right? Like if they're already listed as parents, then we know we're done. They're already in the group, right? And this may be confusing, but like the way to think about it when you're doing this is like if maybe it won't ever happen in this case, but I don't know. It feels a little bit like inbreeding. Like imagine if we have like this grouping happening, and then we say, oh, I want to add this, I want to move this dude to this guy. We can say, oh, well, he's already in this group, so we don't need to move him. Yeah, it does feel, I don't think that will ever happen. But in a disjoint set, it could when you're creating a new union. The union, again, I should say, this is why it won't work if there's multiple relationships. We're replacing the values, right? So we're unioning these two values together, which means it's disassociating it with its previous relationship. So if you've already given a relationship, it's going to lose that. And I think this is why that's there, right? But it was in the pseudocode, and so that's why I added it. But then the idea is we just want to add the smaller tree to the larger tree. So we do this match operation and we say, okay, I'm gonna switch them around based on which one is the smallest. And then all we do is we say the parent of the smallest is the largest. And then we say increment the size of the parent by the size, or the largest by the size of the smallest. And this size is used to track like how big the group is, right? Or the rank. I think sometimes they called it in the program. The idea behind the rank is it will help you like determine which ones should be attached to which for like simplicity's sake, right? Like obviously you want the smaller to go into the bigger because that infers like less time moving and mapping them over. And so what does that move happen? What does this find? That's what this find does right here is like what this find is doing is more than just finding the parent. It's like associating the parent with this value and all of its other values. So here's how that works. Here's the find one. We say, okay, if the parent of I is I, then I just return I, right? So if I go say, hey, what is the parent at 1 and it's 1, I just return it, right? Because now I'm my own parent, so we're done. Eventually we'll get to this point, right? Because this is recursive, so I should probably add that. Maybe that's inferred in the solution, because if you think, or in the thing, because again, if you think about like when we had the, the 1, the 4, and the 6, and the 1, 1, or 1, 1, 4, and we were trying to find this one, right? We were going to place 4 here, and we went here, and then we went here to find it. Like that's what this thing is doing, right? Just to be clear. So if we found our parent, we're done. Otherwise, go find this node's parent and set it to I's parent, right? So, and then return that value. This has the idea of like flattening the tree, which is what I talked about before. So imagine as you're, remember originally this one was set to 4, and so we were going to here and to here. We said, oh, let's label this as 1. I actually think it looked like this. Let's do it over here. It was 1 1. What? How do I do this? 1 3 3 4 4 6. Like let's say we had it looking like this. We know the ultimate parent is 1 right here, but we want to update all these values as we're moving, right? So we say we want to put 4 here, and so 4 is associated with 3, 3 is associated with 1, 1 is the root, so we found it. But as we're backtracking up, we can now update these values. We say like, oh, well, the answer is 1, so I'm going to set this one to 1. And now we say, oh, the answer is 1, so I'm going to set this one to 1. And now it's kind of like flattened out the tree. So now all of them link directly to 1. So the next time you call a find on, say, 6, so if we say 8 is associated with 6 and we try and do this work, we'll say 6 is associated with 1. We don't have to go through the rest anymore. We just say 1 is associated with 1. Oh, and now we can update this, right? So we can now set this to 1. I hope that makes sense. So that's what we're doing with this disjoint set, is we're saying as we're finding, we're going to like flatten out the tree so that any future finds will be faster. And why is that? Is because in the union, obviously you have to do all the finds, right? So you find all those parents, and now they happen in like 01 time. They call it amateurized 01 because constant time, because these finds, you do have to shift them every once in a while. There's a couple steps, but then you flatten it out so that future steps are always just a single recursive iteration. And then when you okay, so now when you join two trees though, like if there were two disparate parents, now it kind of like you've like hooked two together. And can I describe this one? Like, let's say you had a relationship of 1 and 2, and then 3 and 4, and now you want to say, 4 is actually related to 2, as so what that means is like you actually want to put I don't know, let's put 5 up here as well. You want to like hook 4 to 2 like this, which means that ultimately it should go to 5, right? So what the graph will look like is it will go 5, 1, 2, 4, 3, and like this one will be 5, this one will be 5, this one will be 5, and then this one will be 2, and this one will be 4. But then the next time you make a call that like maybe it adds 6 to 3, what will happen is it'll say, 3 is associated with 4, 4 is associated with 2, 2 is associated with 5, 5 is 5. It will then go and fix all these ones down here, right? And it will say, okay, now all of these are 5s. And now you've like simplified that like order grouping, right? Is the way to hopefully I'm making sense with all this scratch and rambling. But that's the way the disjoint union set works, is you're grouping pairs together you're grouping like similar nodes together, and then those nodes are like funneling up to a single root, and then you're flattening that out so they're all equally associated to that root. They're at the same like node level or same rank as the other one. So that's the disjoint union set. And the only thing you need to do that's different between part 2 and 3 is, instead of going through all the parent-child relationships and calculating their similarities, you just add them to the disjoint union set. And then all you have to do now is find the largest value, the largest group, right? So how do I do that? Well, we create a hash map, and we just, for each one, we find the root. Like for each of the sequences, we say, hey, find the root of I. And that will say, so it will say, sequence 1 is in group 4. Sequence 2 is in group 5. Sequence 3 is in group 4. Sequence 4 is in group 4. Sequence 5 is in group 8 or whatever, right? So it's going to tell you which group in the disjoint union set is in each thing. Right? So we're building a hash map of like, here's all the values in, say this is 4, and here's all the values in 2. I guess this is my graph algorithm, but so like maybe right here it would say these are all in 1, these are all in 3, and these are all in 4, right? So now I just fill them up in my hash map, and I just say, hey, for all the values, give me the one that's max, that has the maximum length, right? And then if I don't, this one doesn't need to be here because you will find one, but because of the rust, you have to unwrap it. So I say, okay, do an unwrap or this, and then go through each of them and sum up their values, right? So you remember, the problem wants you to return the ID. So we've talked a lot about the disjoint union set. That's the algorithm that's going to help us like find the relationship between these values. And then we build this hash map of all the groups of relationships. And then we find the one that's the largest and then return the sum of their IDs, which is the problem. And that solves it. There you go. That's part 3. So I think overall, this problem wasn't too bad. It was on the order of like an hour and a half I spent solving it, maybe 2 hours, something along that. I had updated, I had a bunch of test inputs, right? So for each of the parts, for part 3, there were 2 different ones that were given. And I think these were helpful because it kind of, the tests were helpful because as I was like trying to get the disjoint union set working, it was actually, I don't have the code in here anymore, but it was really useful to compare the pseudocode with my own code and like spit out. The nice thing about a disjoint union set is you can easily just spit out the union set itself and see the relationships that it's built. So when I'm going through this find relationships, it's really easy for me to see which relationships it built in the disjoint union set. And then I can compare it to what I would expect from what the problem gave me. So in that sense, the day wasn't too bad. Did I look at this one? I don't know if I looked at other people's solutions on this one. But it goes. A9 solution spotlight. So I just want to look and see. I presume this is what everyone else did. But I do like using 4xu82s to represent the scales. It makes a lot of checks just bitwise. Oh, interesting. So I used a vec of characters. This one uses, you just turn on the bit for each A, C, T, or G. That is a cool thing because now you can just AND them together and do their thing. I did something like this for part 3, right? But mine was a little bit different because I was using, my mask was the mask of a parent to a child, right? And so like that allowed me to just find the differences between the parent and the child and make sure the other parent had covered those differences. Yeah, I think we'll probably find that most of these are like in for loops, right? Although this is interesting, you could do it in parallel. I actually can't do mine in parallel very well because I have my callback function. Doing the outer loop in parallel is interesting though. Again, it finishes so fast. Part 3, because there's 500, may make it worthwhile to do the parallel iterator. It didn't occur to me to do Rayon with the parallel in. So like what they're doing is like, again, they're doing like n cubed. They're just doing it in parallel. So that's this part right here in like the find relationships. You have to do all 3 of these. And the question is like, could you do them in parallel like this? This part feels so fast though. I wonder if like this would be the more interesting parallel. interesting. That's something to think about. So it didn't occur to me to do parallel this time. Sometimes with those large n problems, it's one of the first things I go to. So I wonder why I didn't use parallel iteration. Interesting. I rely a lot on iter tools and Rayon. So I wonder how hard it would be to implement parallel iterations like without the standard library. Like for example, the iter tools, I feel pretty confident that I could implement like a counts one, right? Because we've done that before where we've said, oh, take the values and count the ones that return a count, like a hash map of values and the number of times I saw those values, a counter. I feel like we've implemented that before, and so using the iter tools counts feels pretty cool. I have not even thought about how to do like multi-threading in Rust too much, other than just like, oh, I use Rayon or I use, async await. We've done a lot of that stuff. It might be interesting to try and do that stuff just so I feel more confident in it. In some competitions, they don't allow you to use external libraries. You have to use like the standard library. And in those cases, it's almost you may have to choose like a language that has like more features available to you. So anyway, weird ramblings. Probably not that cool. Language Rust. We got a lot of Rustations here. So it does sound like the Rayon does help in part 3, so I could potentially get this 155 down quite a bit. Oh, interesting. So they do the same thing as like the first one is they say we're going to use 4 U28s because there's 4 values, but instead of like here's all the A's, here's all the C's, here's all the G's, here's all the T's, like each 4 bits of the each 4 bits represent a bit set or a bit mask itself of A, C, G, and T. And then because there's 128, you just have to have 4 of those. So it's like scales all the way down. So you can you do operations over the 4 array of 4 to do it. That makes sense. Okay, and then you can ask interesting things like is child. So given A, B, and C. Yeah, a lot of this is similar to what I've done. It's just now you're using bits as opposed to using vec of car. And I don't think it applies in this day, but in the next day in quest 10, I've just finished, there's a lot of times where you have to you're actually doing a lot of iterations, and so it helps to minimize this. I mean, if you think about it, I did for part 3, I do kind of minimize it with the find relationships. I turn it into, well, I guess I do it for part 2 as well. But again, I think what happened in part 2, I was able to solve it with like just the naive approach of like doing the n cubed and calling the is parent. That worked just fine. It didn't in part 3 because there were 500. And so that's where I optimized it here. And I guess I do use a bit mask just a little bit differently. Although let's see, they may do it. Yeah, no. Oh, they do. Yeah, so this is a similar solution to what mine is, right? Is they say go through each of the DNAs and pre-calculate their score and then find out if they would be a child. Although it's not quite the same, but it is similar. you can see in the end, it's still like, here's a for loop, here's another for loop, a double for loop, and then here's another for loop. I guess the thing that makes it faster is like your first loop is only finding the ones that could potentially be a parent. So like what they're saying is if more than 60 of their values are similar, they might be a parent, and so it's worth checking. Like if there's only one of them, maybe it's saying it's highly unlikely that it's a parent, so don't try. That's an interesting heuristic. It probably works for the problem itself, but you could imagine a case where you say, like I look a lot like my mom. I look more like my mom's side than my dad's side. So maybe it's 80-20 for some people, and so that wouldn't work in all the cases. So you probably just have to tweak this number to get the right one. But yeah, that's a cool idea. It's like, can you like minimize the parent, the number of parents you have to check, right? So again, that's whenever you're doing something that's like n cubed or n to the fourth or whatever, something that's starting to get really big. One of the ways you can optimize it is say, okay, well, it may still be n cubed, but how do I like minimize the amount of effort that happens in there? And one of it could be, okay, in my inner loop, how do I simplify that to the least amount of work I have to do? And in my case, I felt like, oh, well, if I do, maybe I do something that's n squared, but it's so much cheaper to do that n squared when what happens in the n cubed is just a couple of bitwise operators, right? Bitwise operations. Um, in this case, the other way to do it is what they're doing, which I think is a worthwhile thing to do, is to say, okay, well, maybe it's n cubed ish, but what if I could make n for the outer loop like n over 2? And then it's still, big O n cubed, but because we've optimized like the outer loop substantially, it makes it eliminates a lot of the work. If that, I hope that makes sense. So that's a cool way to do it. Brute force for parts 2 and 3 represent the DNA as a bit mass sorted in a pair of U-joint weights. So there's still O and 3. 60 to 6. Choose a child, sort other ducks in descending order of solidity. Oh, this is cool. It's like an exit early. So if you sorted the ducks by descending order, there's no need to check. Like if parent one's similarity is 50 and parent two's is 50, you don't have to continue checking because there's no way, even if that set was disjoint, you'd still only get 100. So that can be, I can see that being really helpful there too, right? So because it's sorted, you go through like the highest similar ones to try and find. And that's actually a cool idea too, because what it means is if you have them sorted in descending order, you're tackling the most similar ones first. And so you're much more likely to find a parent-child relationship with the ones that are like highly similar. That seems true, right? It'd be very rare that you get like the cases where like, again, none of them are. It's a similar to like the looking for the 60, but I think this one's like more generic in the sense that like I'm not looking for a specific value. I'm just looking for, I'm just going to sort them in such a way that it makes them more likely to be found early in my second loop. I like it. Very cool. Okay, and so now we keep a list of like joined families. Okay, so you're kind of doing this all in the same one. So when you find a relationship, you find also the family that that relationship is associated with and add them to that family. So then when you're done, you just say, hey, give me the largest family. And then I can iterate over their IDs and return them. Very cool. I felt good about the disjoint set because I never implemented one before. I do think there's other way. Again, I think once you have the relationships, like the total number of things that you're working on is relatively small. That like just things like this are probably really fast, and so actually doing a disjoint union set is probably not necessary. Yeah, it looks like a lot of people had the same ideas. Like, what if you just put a bunch of values, put a couple ints together, and represent all the values, and then you can do bitwise operations really easily. I definitely think this is one to think about, right? Yeah, you can see here, there. I actually like this is really cool, creating like these bit things. There is like a bit set crate in Rust used before. But this is really interesting, right? Like this is a cool way to say like, oh, here's where they are and how to set them. So very cool. Standard union fine. Well, fine might go version. Rayon just because first ever. Oh, this is a cool SimD one. Yes, this is one that you could definitely do with SimD because you're using like if you're using like multiple ints, SimDing the ints is very cool. Yeah, so they SimD use 64 by 4. If you've never used SimD, any SimD things, you're probably okay not to. But it is a cool optimization. At a high level, the way that it works is, and I think some of these are only available in the nightly of Rust, but like other operating system or other languages can do SimD as well. The idea is the CPUs have gotten like absurdly good at doing a calculation. And they now have tools where they say, hey, do that calculation over these 4 values, and it will, instead of like doing it 1 2 3 4, which is, I mean, it's still absurdly fast, it'll do all 4 at the same time. And so you call like a special, it's like you actually see it in the machine code. You call instructions that are associated with, or I guess it's in the not in the machine code, but like the oh man, the name's gone away from me. Anyway, you see the instruction that actually says, here's the 4 values, and push the 4 values through. Assembly. Wow, I don't know why that took me so long to come with that. You actually see it in the assembly where it says like, okay, here's, RAX, RBX, RCX, RDX, and put them all in together. Call this calculation on the 4 of them, and it'll do them all 4 at the same time. Very cool. But yeah, okay, union find is another term for disjoint set, right? So it looks like in the end they did the same thing. This one, it sounds like it would definitely be you could probably optimize this 155 with Rayon and get it down to really fast by doing it in parallel. That's the power of modern processors, right? Yeah, you do have to do some weird stuff. I think you just assume, like a lot of times what I do is I assume just based on the computer. When I was doing the SMD stuff, I just said, oh, I know my CPU supports these operations, so I'm going to support those. That is the trick with the SIMD, is like it doesn't fall. It's very like, oh, we're just going to give you the straight up equivalent of the assembly language, whereas a lot of them get abstracted. And I think some languages do this. Like, I'm trying to think of which ones they are, but you can do, like, for example, string finds. Did anyone ever do the 1 billion row challenge? That would be interesting. Let me know if you did. I did it in, I think, Go and Rust to see if I couldn't get it down to about 1 second. And, I think that was the idea, is can you get it into the 1 to 2 second range? I think I was for both of them. SIMD was really good because you could do like string comparison operators, because at the end of the day, strings are just U8s. And so if you're searching for a specific U8, doing that over with SIMD, you can do 8, 4, or whatever comparisons over at a time to find the right one, and that speeds it up. It's a big enough change when you're doing 1 billion rows that it makes it faster. Yeah, so you can see the different things here. That's pretty cool. Okay. Let's just look at anyone else? Brute force, convert parent child IDs to sets, then looped over till only disjoint sets left. Classic union find. Okay. Oh, they just kind of did the union find here. Okay. Let's find another language. I'm surprised Python doesn't have a union find. I think it's probably, I would suspect that yeah, it's probably in the list of algorithms for competitive programming. Being able to do a union find or a disjoint set is like powerful. So that's why it solves some problems, and you just need to solve it. You just need to know how to do it. So that's why I implemented it today, because I was like, oh, it would be nice to or I guess for this quest, it would be nice to go through it. I've heard of them before. I think I used a library the last time I tried it. But I thought, oh, I should probably learn how to do it just so I understand exactly how the algorithm works. So that was fun, made it worthwhile. Brute force. Is it like literally brute force? I have no idea what a nucleobase is. This person probably has some genetics experience. Looks like they did a mask size 4 again. Okay. It would be interesting to do a comparison of, is this way faster? Because I think doing the n squared is pretty fast. If you find all of the similarities between all of the pairs, then you can go through it really fast. It would be interesting to know which one's better. It actually, I don't think anyone did it quite the way I did. They definitely found a lot of optimizations, but remember, mine was we got to do n cubed, and I think that's a fact, right? Like, I don't think there's any faster way to do this. You just have to do the n cubed, and so the question is, how do you optimize that n cubed? And it sounds like a lot of people did the work inside there. They just used bit masks as the scale values, whereas I said, okay, give me all the scale values and I'll create bit masks and do diffs between them. So it is a little bit different, but I think at the end of the day, they both had the same goal of how do you minimize the work that happens in the n cubed loop. Oh no, they do use a union find here. I mean, maybe what they meant by brute force is the n cubed is just a given. You just have to do it. Okay. Unim. Very cool. Spent time optimizing only to make it slower. Man, I tell you, I've done that before. Don't get me started on Quest 10. I mean, I guess you'll see it in the next video, but. Oh, this looks similar, right? Like you find their similarities and you track them. So then when you're solving part 2 or part 3, you can like reuse that similarity list to do the thing. Okay. Okay, I think we spent enough time on this one. It was a fun problem. I had a lot of fun doing it. I mean, definitely there were bugs that I had to figure out and fix, but what I would say is the overall goal is, you know, recognizing, oh, I just have to try all the things to do all the relationships. So how do I optimize that? Seem to solve it. You know, sometimes there's days where you can say, oh, here is the I found this trick with the input, and so it's not actually n cubed. It's just you know, I can solve it in n squared time or whatever, and then it makes it substantially faster. That's definitely one way to do it. So but I think it looks like, at least for most of the solutions, was you just have to do all the parts. And so as you're doing all the parts, you know, for part 2, find the similarities and sum them up. For part 3, do like a union find or a disjoint set and solve it. So there you go. Thanks everybody. I had a lot of fun doing this. Hopefully you had a lot of fun watching. And yeah, we'll be back for Quest 10. So talk to you later. Bye everybody.